All right, okay. So let's first review the primordial transformation that we discussed last week, okay? So in this kind of problem transformation, we discuss linear programs. So in the linear program, we have some objective function, okay? So some function that you want to maximize or minimize, and you have some variables, and you have some constraints. And the property about linear programs is that all the objective function and the constraints are linear with respect to the variables here. So you can see that here the objective function is just x1 plus 6x2. So it's a linear combination of the variables, okay? And I'll say the main motivation for this primordial transformation is to find bounds, to find upper bounds or lower bounds. So since this is a maximization problem, so we'll try to seek an upper bound, okay? So the basic idea is to find combinations of the constraints so that we can use the combination of constraints to build an upper bound, all right? So in this slide, we combine these three constraints using these corresponding weights, okay? So by this, we mean we multiply the first constraint by 1, multiply the second constraint by 6, okay? And we just compute the sum, okay? The sum is x1 plus 6x2 is at most 2,000, okay? So this gives an upper bound of 2,000, okay? But I want to find a beta upper bound. By beta, we mean lower because we want to find a tighter upper bound, okay, which is close to some feasible solution, like 1900, okay? So what we did next is to find a different set of weights. So this time, we only consider constraints 2 and 3, okay? And the weights are 5 and 1 respectively, right? So the result is that we can get an upper bound of 1900, which matches the objective value for the previous solution, right? So this says, well, basically 1900 is the best you can achieve, okay? So if you have a solution whose objective function or whose objective value is 1900, then the solution is the optimal solution, okay? So the problem becomes how to find a proper set of weights so that we can use these weights to find the upper bound, okay? So we model this problem as a minimization problem, okay, where the variables are just the weights associated with these constraints, okay? So after you find the weighted combination of the constraints, you get some inequality like this, okay? So in this inequality, you can see that, first of all, the variables x1 and x2, now they have some new coefficient in terms of y's, okay? And so this is on the left-hand side. And on the right-hand side, we have, again, some weighted combination of y, okay? So the basic idea is that we want to find, so this right-hand side will be the upper bound, okay, that we want to minimize. So the objective function becomes to minimize the right-hand side of the weighted combination of the constraints, okay? So we want to minimize the right-hand side, okay? And we want to make sure that this whole constraint gives us an upper bound for the original objective function, x1 plus 6x2. So we have to ensure that the coefficient of x1 is at least 1, and the coefficient of x2 is at least 6, okay? So that's why we have these two constraints here. So y1 plus y3 should be at least 1. And y2 and y3, the sum should be at least 6. Okay? So given these two constraints, we can ensure that this, the whole inequality, gives us an upper bound for the original problem or the primal problem. Okay? And finally, because we multiply these constraints by these weights, and we do not want to change signs. Okay? So all of these signs are just less than or equal. Okay? We don't want to change it to greater than or equal. So we have to make sure that all the variables are non-negative. Okay? They are greater than or equal to 1, equal to 0. So this is the corresponding dual problem for this primal problem. Okay, so the general principles to perform the transformation is to first, for every constraint, we have to create a corresponding dual variable. Okay, so that's the first step, and then we're going to just compute the weighted combination of the constraints, where the weights are just the dual variables. Okay, so we're going to compute this weighted combination. Okay, so this one. Okay, so this is the weighted combination of all the constraints, where the weights are just the dual variables. Okay, so this is actually an inequality. Okay, so we're going to minimize the right-hand side. Okay, so the objective function is to minimize the right-hand side. Okay, and then we have to make sure that the coefficient in the objective function of the primal problem. Okay, so here 1 and 6. Okay, so this should be a lower bound for the coefficient of x in the weighted combination. So that is, we have to consider the left-hand side. Okay, so the coefficient in the left-hand side should be at least the coefficient in the original objective function. Okay, so the coefficient of xi in the left-hand side of the weighted combination, okay, should be at least the coefficient of xi in the original problem. Okay, and finally, we have to make sure that all the dual variables are non-negative. Okay. Okay, so if we consider like the general form of linear program, then we can write the objective function as c1x1 plus c2x2 up to cn xn. So here we assume there are n variables, okay, x1 up to xn, and we have m constraints, okay, where each constraint is in the form of ax plus a11x1 plus a12x2, and so on up to a1n xn, and this is at most b1. Okay, so this is the first constraint, and we have in general m constraints. Okay, so for every constraint, according to our previous steps, the first step is to create a dual variable for every constraint. Okay, so y1 for the first constraint, y2 for the second constraint, and so on. Okay, so whenever you need to write the dual problem, I'll say the first step or the easiest step is to write the objective function. The objective function is quite easy. You just combine this right-hand side, that is b1, b2, up to bm, with the dual variables. Okay, so it's like compute the inner product of these two vectors. Okay, so this is just b1 y1 plus b2 y2 up to bm ym. Okay, so this step is quite easy. Okay, so to find the objective function in the dual problem, you just compute like the inner product of these two vectors. Okay, so that's the objective function. Now for the constraints in the dual problem, the right-hand side is also quite easy. Okay, the right-hand side are just the coefficient of x in the original problem. Okay, so you can see that the right-hand side are just c1, c2 up to cn. Okay, so for every variable, you have to create a corresponding constraint. So in a dual problem, we have n constraints. So in the primal problem, we have m variables and m constraints. Now for the dual problem, we have m variables and n constraints. Okay. The reason that we have n constraints is that we have to make sure that the coefficient in the primal problem is like a low amount for our weighted combination. Okay, so we have one constraint for every variable in the primal problem. Okay, and then we just consider what is the coefficient in the weighted combination of the constraints in the primal problem. Okay, so we start with x1. Okay, so what is the coefficient of x1 after you compute the weighted combination of these m constraints? Well, the coefficient of x1 will be just a11 times y1 plus a21 times y2, and so on up to am1 times ym. So this one, okay? So it's like we perform the transpose of this matrix, okay? So in this primal problem, we consider like row by row. But in the dual problem, we're going to consider column by column. Okay. Yep, and finally, all the dual variables are non-negative. Okay. Yeah, and also there's a quite compact way of representing this primal dual transformation using matrix and vectors. Okay, so we can use this capital A to denote this coefficient in the constraints. Okay, so this is A, and the variables x1, x2 up to xn, this is just the vector x. Okay, so this one, this is just ax. Okay, so ax is at most b. So B is just this column vector consisting of all the right-hand side of the constraints. Okay, and yeah, the objective function is just like the inner product of C and X, and all the variables are non-negative. Okay, so this is the primal problem, and the dual problem has a very similar form. The only difference is that we take the transpose of the matrix A. Okay, and now the variable becomes y, and in the dual, in the objective function, the coefficient becomes b. Okay. All right. So last week we just wrote down this inequality, that is the weak duality. So in this weak duality, you have one feasible solution x, so that's for the primal problem, and say you also have another feasible solution, but this time for the dual problem, that's called y. Okay, so what is CTX? So C transpose x. So this is just the objective value. Okay, the objective value of x. Okay. And similarly, B transpose Y is just the objective value of Y. Okay. So this inequality says the dual feasible solution gives an upper bound for the primal problem. Okay. But here, the assumption is that both X and Y, they are feasible. Okay. They are feasible with respect to their problem. Okay. So for X, it is feasible for the primal problem, the original problem, and for Y, it must satisfy all the constraints in the dual problem. Okay. So you have to have these assumptions so that you have this relationship. Okay. So next we're going to prove this. Okay. And the proof is quite easy. Okay. But before we start, are there any questions? 有问题吗？就是我们刚刚做的事情，大概是很快的把我们上礼拜讲的东西复习一下。所以我们上礼拜主要就是讲一些问题的转换这样子。OK， 然后这边忘掉证明的话，这边要传递的资讯就是，如果你有一个本来的问题 ，OK， 然后你有本来的问题的随便一个 solution， 假设那个 solution 叫 x， 那你当然可以去看一下，哎，那个 x 它对应的值会是多少？那个值就是那个 objective value 会是多少 ？OK。那如果你手上有另外一个 dual problem 的 solution y，OK， 那如果那个 solution 它也会满足所有的 dual problem 的限制，那一个 dual solution y 它的值就是它的 objective function， objective value 就会是 upper bound， 就会是本来那个问题的 upper bound，OK。所以每一次你想要，你手上有一个问题，你想要知道你的解是不是最好的，你都可以试着用这套问题的转换去找，看有没有tight 的 upper bound，OK。Okay. So let's prove. So let's start with the left-hand side. Okay. So this is just the objective value achieved by x. Okay. So we want to find some upper bounds for this weighted combination. Okay. So this is just a weighted combination of the variables x. Okay. So what we do here is that we find some upper bound for the coefficient ci. Okay. So to find the upper bound, we can use the dual constraints. So the first dual constraint gives us an upper bound for C1. Okay. So similarly, the second constraint gives you an upper bound for C2. Okay, so that's why we have this inequality. Okay, so what we do next is to rearrange these terms so that we can put together all the terms related to y1 and then put together all the terms related to y2 and so on. Okay. So now, which terms are related to y1? So we have a11x1 plus a12x2 Okay, so these are the terms related to y1. Okay. Now let's consider y2. Okay. Okay, so that's all the terms related to y2. So finally, let's consider ym. Okay, sorry, this should be equal. Okay, because we just rearrange these terms. Okay, right. So next, let's try to find an upper bound for the coefficient of y1. Okay. Okay, so you can see that the coefficient of y1 is exactly the left-hand side of the first constraint in the primal problem. Okay, so because x satisfies the primal problem, okay, all the constraints in the primal problem, so we know that a11 x1 plus a12 x2 up to a1 to a1n xn will be less than or equal to b1. Okay, and similarly, the coefficient of y2 is a21 x1 plus a22 x2. Well, this term, this sum, is at most b2. Okay, so we have this relationship. Okay, so this is due to the assumption that x is a feasible solution for the primal problem. Okay. And for this inequality, we use the assumption that y is feasible with respect to the dual problem. Okay. So that's why we need those two assumptions about the feasibilities of x and y. Okay. And now this term, this sum is just b transpose y. Okay. So this finishes the proof. Okay. Okay. Are there any questions? Okay. So recall that the reason we want to discuss primordial transformation is because we want to figure out why can we think of vertex cover when we consider matching. Okay, so what is the relationship between matching and vertex cover? Okay, so next we will consider the linear program for maximum matching. Okay, so suppose this is the input. Okay, so we want to find the maximum matching. Okay, so here edges do not have weight. So what we want to do is to maximize the number of edges in the matching. Okay, so the maximum matching problem. All right, so how to model the maximum matching problem as a linear program? 所以我们现在要做的事情就是，因为我们前面在谈的是 linear program，OK，linear program 就是有 objective function 有限制 ，OK， 然后你要去 maximize 或 minimize 什么东西这样子。那我们接下来要做的事情是要想办法把 matching 这个问题转成 linear program，OK， 那这样子转成 linear program 之后，我们就可以去看它的 dual problem。Okay. So I said the first step is always to decide the variables. So what are the variables? Okay. So because in a problem of maximum matching, we need to decide for each age, should we choose it in our matching? Okay. So for every age, we will create a corresponding variable. Okay. So in particular, this will be a binary variable, indicating like if it's 0, this means this age is not chosen. If it is 1, then this age is chosen. Okay. Okay. So for every age, EI will create a variable XI. Okay. So the physical meaning of xi is that if xi is 0, then we do not choose it. Okay? If xi is 1, then we'll choose it in our matching. So the set of ages that we choose are just the variables that are assigned 1. Okay? Okay, so these are our variables. So the next step, after we have defined the variables, I'll say the next step would be to decide the objective function. Okay, so because this is a maximization problem, okay, so because you want to maximize the number of edges, so intuitively it should be to maximize some objective function. And what is the objective function? Okay, so now because we know that xi equals 1 if we choose it, and it equals 0 if we do not choose it. So a natural objective function will be just to compute the sum, okay? Take the sum of all these variables. If, for example, this sum is 3, then this means 3 edges are chosen, okay? And we want to maximize this sum, okay? By maximizing this sum, we can maximize the number of edges that we choose in our matching, okay? All right, so this is the second step, okay? So we have determined our objective function. The next step, which is also the last step, is to define the constraints, okay? So what are the constraints in maximum matching? What constraints do you need to consider when you choose edges? Well, the only constraint is that these edges that you choose, they cannot touch each other. They cannot be adjacent to each other. In other words, for every vertex, you can choose at most one of the neighboring edge or one of the incident edge. So for example, for V4, so 3 edges, E1, E2, and E3, are incident to V4. But among these 3 edges, you can choose at most 1. Okay? So this says if we just consider V4, then x1 plus x2 plus x3 should be at most 1. Okay? But actually not just V4, we have to consider every vertex. Okay? So for every vertex, we can choose at most 1 of its instant edges. Okay? So the corresponding constraints for this particular instance will be, we'll first start with V1. Now because V1 only has 1 instant edge, that is E1. Okay? So the constraint is just x1 is at most 1. Okay? And similarly for V2, because it only has 1 like neighboring edge, so yeah, x2 is at most 1. And then when we consider V3, so among all these 3 edges, we can choose at most 1. So the constraint will be x3 plus x4 plus x5. So their sum should be at most 1. So we can use this constraint to enforce that at most 1 of its instant edges is chosen. Okay? So that's for V3. And for V4, similarly, we have x1 plus x2 plus x3 is at most 1. Okay? So the idea is still the same. Okay, we want to make sure that at most 1 of its edges are chosen. Okay? So this one is for V5. Okay? And the last one is for V6, okay? So because V6 only has 1 instant edge, so the constraint is x5 is at most 1, okay? Okay. So this is, okay, so this is the, well, this is not a linear program, okay? Because we have this binary constraint here, okay? But at this moment, we just ignore this one, okay? Because what matters in the primordial transformation is we have to consider the objective function and the constraint, okay? So we'll just focus on the constraint and objective function, okay? 所以这边就做了一个蛮简单的事情，就是把 maximum matching 转成linear program， 然后这个动作我觉得在很多的 optimization 的问题都会出现，就是每一次你有一个 binary 的选择的时候，就是要或不要，选或不选 ，OK， 买或不买，你都可以先从这种0、1的 binary 的 variable 出发 ，OK， 所以一旦你有了这个 variable 之后，你就可以开始去想你的目标 objective function 是什么，还有你的限制是什么 ，OK？ 所以我觉得第一步都是从变数出发去思考一下，在你这个问题里面变数应该会是谁。那有了这些变数之后，你就可以去想 ，OK， 目标是什么？那像在 matching 里面，我们的目标就是要越多的 edge 越好 ，OK？ 所以通常你的目标一定就是会需要跟这个 xi 有一些连结。那因为我们这边的物理意义就是这个1就代表有选，0就代表没有选，所以它的目标事实上就是去把这些 x1 一直到看你有几个 edge，OK， 就全部把它加起来，这个算出来的数字就会是你选到的 edge 数。对，然后接下来就是限制 ，OK， 所以限制这边如果是 matching 的话，我们刚刚说的就是边不能碰在一起 ，OK， 如果你从边不能碰在一起这个角度，就可能这个限制是就会比较难写一点 ，OK， 因为像这边有3个边，你要怎么写？所以它们不能碰在一起，所以这边事实上 关键的角度是要从 vertex 去出发 ，OK？ 所以如果你的视角稍微改一下，把它变成从 vertex 出发的话，这里的限制其实就是对于每一个 vertex 而言，它相邻的边最多只能选到一个。那你要怎么把这种限制式转成这种不等式？那这边就是把这些 variable 它相邻的边的对应的 variable 全部加起来 ，OK， 然后小于等于1。那这样子再搭配上面这个，就是 xi 只能是0或1，就可以确保说，譬如说像这个是针对 v3 的限制，这个它就会保证说，不会同时 x3 跟 x4 都是1，不会 ，OK， 最多只有一个x3、x4 或 x5，最多只有一个会是1。OK， 所以这个是一些我们在做这些问题的 modeling 的时候会常用的技巧。OK， 这个等一下我们会再看更多例子，大家就会比较熟悉。Yeah, 就是 so whenever you have this kind of binary constraint indicating that this variable should be only just 0 or 1, then this variable is not continuous. So the key point about this linear program is that all these constraints should be continuous. Whenever you have this like discrete constraint, we'll say this is a mixed integer linear program. Okay, so we're going to add this mixed integer because for some constraints, we need, for some variables, it must be some integers like 0 or 1. Okay. But in general, if the problem is modeled as this mixed integer linear program, then in general this problem is NP-hard. Okay. So, but for maximum matching, actually we can replace this constraint. We can replace it with this linear constraint, okay, indicating that xi is at most 1 and xi is at least 0. So xi cannot be negative, okay, but at most 1. Okay. So if you replace this binary constraint with this one, then this becomes a linear program. And you can always solve linear program in polynomial time. Okay. Yeah, so the nice property about this linear program is that the solution is integral. What do I mean by this is that if you solve this problem, you find the optimal solution, then the optimal solution, all these x, will magically become integers. Okay, so this is one nice property about this linear program. 所以有一些 linear program 我们会叫做它是 integral， 它们有 integral 的 solution。OK， 那刚刚这位同学问的是说，如果你今天的这个 xi 的限制本来是0、1，这个就不是 linear program。OK， 所以每一次你的限制是有这种离散的 ，OK， 0或1或0/2都 ，anyway， 只要你的solution 的范围不是连续的，那它就不是 linear program。OK， 那一般来讲，如果是这种离散的 ，OK， 0或1这种，这个问题就会变成是 NP-hard。OK， 就目前没有人知道怎么在 polynomial time 把这个问题解掉。可是对 maximum matching 这个问题而言呢，就是一个好的特性就是，如果我们把这个 xi 这边是说只能是0或1嘛。我们把它 reduce 成这个限制，就是 xi 它不是0或1，它现在变成是0到1的任何一个数，也可以是0.3、0.7、0.8这样子 ，OK， 那这样它就会变成一个 linear program， 然后 linear program 是有 polynomial time solution 可以解的 ，OK， 那除此之外呢，就 maximum matching 的问题有一个好的现象，就是它的最佳解就是会有这种 integral 的现象 ，OK， 就是它的 solution 会是整数 ，OK， 所以你就可以用 linear program 去解决 maximum matching 的问题。对，好不好？这样 ，OK， 有问题吗？这刚刚后面那个不是我这门课主要 cover， 我这门课主要 cover 只是要讲后面的转换，怎么把 matching 转成verse cover，OK，所以刚刚这个算是额外补充。所以我刚刚说，如果你要做 primal dual 的转换，我觉得关键就只有在你的 objective function 跟你的 constraint。一旦你有 objective function 跟 constraint， 你就可以开始做那些转换 ，OK， 那你就可以看出来我们怎么从 matching 转成 verse cover。有问题吗？Okay, so let's find the corresponding dual problem. Okay, so let's just focus on the constraints and objective function. Okay, so first step, to find a dual problem, we create dual variable. Okay, so this is easy. So for every constraint, okay, so recall that this first constraint is respect to is with respect to V1, the first vertex, and the second constraint is associated with the second vertex V2. Okay, so and so on, because we have 6 vertices, so we have 6 constraints, which means we have 6 dual variables. Okay. Second step, okay, so we find the objective function in the dual problem. And the dual problem for maximization problem is always a minimization problem, okay? So we want to minimize something, okay? In particular, we want to minimize like the right-hand side of the weighted combination of these constraints, okay? So I said earlier that the objective function for the dual problem is simple, okay? We just compute like the inner product of B and Y, okay? That is the right-hand side of the constraint and the dual variables, okay? Okay, so now you can see that the right-hand side are just 1, okay? So the objective function is just y1 plus y2 up to y6, okay? In other words, it's just the sum of the dual variables, because all this right-hand side of the constraints are just 1, okay? Okay? So this is the second step, the objective function, okay? And the third step is the constraint for the dual problem. Okay. So for the dual problem, we can first consider again the right-hand side. So what is the right-hand side? The right-hand side is just the coefficient of x in the primal problem. Okay. So because here we have 5 variables in the primal problem, which means we have 5 constraints in the dual problem. Okay. Okay. So 5 constraints. Okay. Corresponding to the 5 variables in the primal problem. And the right-hand side is just the coefficient of x in the primal problem. Okay. And here the coefficient is 1, okay, for every x. Okay. Okay. And then we have to figure out the left-hand side. Okay. So what is in this box? So in this box, we have to put the coefficient of x1 in the weighted combination of the constraints. Okay, so let's find all the terms related to x1. Okay, so we have this. Okay, so x1 appears in the first constraint and the fourth constraint. Okay, so if you compute the weighted combination, then the coefficient of x1 will be y1 plus y4. Okay. Okay, and recall that this is for x1. Okay, so this is to make sure that the coefficient of x1 is correct. It is an upper bound for the original objective function. Okay. In other words, this is related to v1. Okay, so this constraint is for v1. Okay. Okay, so next, the coefficient of x2. Okay, so let's find x2. Okay, so x2 appears in these two inequalities. Okay, so first for v2 and for v4. So y2 plus y4. Oh, sorry, I made a mistake. So this is for x1, but this x is related to edges, not vertices. So this is for E1. I'm sorry. Okay. So similarly, this is for the variable x2, and x2 is related to E2. Okay. So this constraint is for E2. Okay. Sorry, I made a mistake saying that this is for V1, but actually this is for the first edge, not the first vertex. Okay, because these vertices, they are created for every edge, not for every vertex. Okay. Okay. Let's take a break. Okay, and when we come back, we're going to finish the dual problem. All right, so before we start, I have a few announcements to make. related to the midterm exam. So tonight, I will upload the first assignment to Moodle, okay? And you have 1 week to complete the assignment. So next week, next Tuesday, we're going to discuss the solutions for the first assignment, okay? Okay, and we will have our midterm after 2 weeks. Okay. So the exam is open book, so you can bring any notes, any textbook, but you cannot use the internet, including Google, ChatGPT, or other AI assistants, okay? So basically, no smartphone, no notebooks, no electronic devices, okay? But you can bring any paper or textbook or notes, okay? No tablet, okay? Okay, so no electronic devices. 所以很重要，所以我在说下礼拜我们会检讨第一次作业 ，OK？ 所以今天我就会上传第一次作业，然后大家需要在1个礼拜之内完成，然后2个礼拜之后我们就会有期中考，然后期中考 open book， 所以你可以带任何随便你喜欢的书，你的笔记随便都可以 ，OK？ 当然不能用电子设备，不能用手机，不能用笔电 ，OK？ Okay, so back to the transformation. All right, we have completed the first 2 constraints, that is related to x1 and x2. All right, so the third one is for x3. That is for E3, okay? So we have to find out the coefficient of x3 in the weighted combination of the constraints. So x3. Okay, so x3 appears in the third and fourth constraint. So we have y3 plus y4. And for x4, so x4 appears in the third and fifth. Okay, so finally, for x5, so x5 appears in the third and last constraint. Okay. Okay. And don't forget about the non-negative constraint. Okay, so all these dual variables have to be non-negative, okay? So this is the corresponding dual problem, okay? Okay, so now we have the dual problem. Then we have to figure out the physical meaning of the dual problem, okay? So what is the physical meaning of the variables? And what is the physical meaning of these constraints, okay? So we have to create some meaning for these constraints and objective function and variables. Okay. So let's start with the constraint. Okay. So recall that this constraint is for the first age, E1. Okay. And we have Y1 and Y4. Okay. So recall that these dual variables are created with respect to vertices. Okay. So this is like we have Y1, Y2, Y3, Y4, up to Y6, okay? So these are the variables associated with the vertices, okay? Now, the first constraint says Y1 plus Y4 should be at least 1, okay? So this is for the first constraint, okay, for E1. Well, so I think the relationship here is quite simple, okay? So we consider the endpoints of the edge, okay? And we compute the sum, that is Y1 and Y4. And their sum should be at least 1, okay? And so this is for the first constraint. And for the second one, that is for E2, okay? So E2 has endpoints V2 and V4. So you can see that the left-hand side of the second constraint is exactly the sum of these two variables, Y2 plus Y4. Okay, so I think the general form of the left-hand side is just the sum of the dual variables of the two endpoints. Okay, so you have the age, and then you have the endpoints, and you just compute the sum of their dual variables. That is the left-hand side, okay? And the right-hand side is just 1, okay? So if we further impose the constraint that y can only be 0 or 1, okay? Then this becomes like a binary variable where every dual variable y can only be 0 or 1. And then you can interpret these dual variables as, so if y is 1, this means not chosen. And if y is 1, then this means EI is chosen. Sorry, VI is chosen. Okay. So in this dual variables, in this dual problem, the action is to pick some vertices, okay? And the constraint is that for every age, you have to pick at least one of its endpoints, okay? So for E2, Y2 plus Y4 should be at least 1. So this means you have to pick either, you have to pick V2 or V4, okay? You can pick both, okay? But you cannot ignore all these two endpoints. You have to pick at least one of them, okay? So the physical meaning of this dual problem is, well, at least from the constraint says you have to pick for every age at least one of the endpoints. So that's the constraint. And what is the objective function? So the objective function is to pick the smallest number of vertices so that you can satisfy the constraint. And here the constraint is that you have to pick at least one of the endpoints for every age, okay? So we all know that this is just vertex cover, because in the problem of vertex cover, we have to cover every edge. And to cover every edge, we have to find or pick at least one of the endpoints for every edge. And the objective is to use the smallest number of vertices to cover the edge, to cover all the edges. Okay? So this is why we consider the vertex cover problem. Okay? So actually, we can consider a more general problem. Let's consider the maximum weighted matching problem. Okay, so in maximum weighted matching problem, edges have weights. Okay. So once again, let's start with the primal problem. That is, we try to formulate the maximum weighted matching problem using mixed integer linear program. Okay. So again, the first step is always to define the variables. So again, because in maximum weighted matching problem, we have to decide for every edge, should we choose it in our matching or not. Okay. So we have the same set of variables, xi. Okay. So if it is 1, this means ei is chosen. Okay. And after we have the variables, I'll say the second step is to figure out the objective function. Okay. So what is the corresponding objective function? 所以我们接下来考虑就是比刚刚那个 maximum matching 再稍微更广义一点的问题，就是 maximum weighted matching。OK， 所以在这边大家回忆一下 ，OK， 这个问题就是你要找到最大的 weight 的 matching。OK， 那什么叫最大的？就是这时候边上面都有 weight， 然后我们选的 matching 要是那个 weight 最大的，就是 edge 的权重总和最大的那一个。OK。然后我们的目标就是要先把它转成这种mixed integer linear program， 然后我们等一下再去看 dual problem。Okay. 好，所以我们刚刚已经确定说我们的 variable 就跟前面没有 weight 的版本是一样，就是因为我们这个问题它的要控制或要决定的事情就是哪一些边要选，哪一些边不要选。OK， 所以 xi 一样是我们的变数，然后物理一样没有变。所以下一个阶段就是 objective function，OK， 目标会是什么？所以这边的目标会是什么？ Right. So this time the objective function becomes a weighted sum of the variables, where the weights are just the edge weights. Okay. So because if you choose E1, then you will get a weight of 3. Okay? So naturally, we will multiply x1 by 3. Okay? All right, so this is just a weighted combination of the variables. Okay? So this is the objective function. And then we have to consider the constraints. So what are the constraints? Well, for maximum weighted matching problem, the constraints are the same. Okay? For every vertex, we can choose at most one of its instant edge. So we have the same set of constraints. So this will be the primal problem for maximum weighted matching. Okay? Okay, so next let's figure out the dual problem. Okay. The first step, again, we create the dual variables. Okay, so we have again y1, y2 up to y6, and we have to figure out the objective function. Okay, and the objective function is once again all the variables times the right-hand side of the constraint. Okay, so we have the same objective function in the dual problem. Okay. Yeah. So next, the constraints. Okay, because we in the right-hand side of this constraint, we consider the coefficient of x in the primal problem. Okay, so this time the right-hand side becomes the coefficient of x1 should be at least 3, okay? At least 3. And the coefficient for x2 should be at least 1. Okay. So in the dual problem of the mixed-bound weighted matching problem, the right-hand side for the constraint are the edge weights, okay? 3, 1, 2, 6, 2, okay? And because we did not change the constraints in the primal problem for the mixed-bound weighted matching problem, so the left-hand side of the constraints are the same. Okay, so we only change the right-hand side of the constraints in the dual problem. Okay. Well, this time we no longer have this binary constraint because it does not make sense. Okay. Because sometimes we have to make sure that these two variables, their sum is at least 6, okay? So if the sum is at least 6, we cannot have this binary constraint, okay? So this is just the dual problem for mixed-bound weighted matching problem. So this is like the weighted vertex cover. Okay, so why? So in this problem, we will assign weight to vertices. Okay, so we assign weight y1 to vertex v1. We assign weight y2 to vertex v2. Okay, we want to minimize the total weight of the vertices. Okay, and the constraint is once again to cover edges. Okay. But this time, to cover an edge, you have to make sure that the weight of the two endpoints is greater than or equal to the edge weights. Okay? So you have these constraints. Okay. So this is exactly the weighted vertex cover problem when we consider the mixed-bound weighted matching problem. Okay? So, yeah. So basically, we the transformation behind matching and vertex cover is this primordial transformation. Okay. Okay, so next I'm going to give you the general form of matching or mixed-bound matching. So let's assume we have xi for h ei, and we have m edges. Okay, so the general form is to maximize just the sum of all the variables. Okay, and because we have m edges, so we consider x1, x2 up to xn. Okay. Okay. And the constraint is that for every vertex, okay, at most one of its instant edges is chosen. Okay. So for every vertex, it's called Vj. Okay. Okay, so in this summation, we consider all the edges such that these edges are instant to Vj, okay? And we'll consider all the possible vertices Vj, okay? So the variables for these edges, their sum should be at most 1. Okay. So you can compare this general form with the constraints here. Okay. So for some of these constraints, you can see that there's only one variable. So this happens when the vertex that we consider only has one instant edge. Okay. So for this one, this is a vertex that has 3 instant edges. So we have to consider all these 3 variables. And their sum should be at most 1. So if the sum is at most 1, then we can know that we can choose at most one of its instant edges. Okay, so this is the primal problem. Okay. Okay, so for the dual problem, we will create a dual variable for every constraint, or for every vertex y, for every vertex vj. Okay. So we have yj. Okay, as our dual variables. Okay, so the objective function of the dual variable, the dual problem, is just like the inner product of the right-hand side of the constraint and the variables. Okay, so because let's say we have n vertices. Okay, so this means we have n dual variables. Okay, and because the right-hand side is just 1 for every constraint, the objective function is just the sum of all the variables. All right. And in the constraint, we have to make sure that the coefficient is large enough compared to the original coefficient. And the original coefficient for every variable in the primal problem is 1. Okay. So for every edge, there's a corresponding constraint saying that the coefficient should be at least 1. Okay. Now, I think the most difficult part in the primordial transformation is to figure out the left-hand side in the general form. Okay. I'll say to do this, the easiest way is to first consider some toy examples to have some simple observation. Okay. After that, well, we know that in the unweighted problem, yeah, okay. So the left-hand side is just the sum of the dual variable of the endpoints. Okay, so take the two endpoints of the H, and their sum will be the left-hand side. Okay, so if this H has endpoints VA and VB, then the two endpoints have dual variables YA and YB, respectively. Okay, so their sum should be at least 1. Okay, so yeah, my suggestion is that whenever you have to create the dual problem in the general form, first observe some simple examples, okay, to have some observation, okay. Okay, so this is matching and verse cover. And by the way, if you want to consider the weighted problem, all you have to do is to add this weight Wi. So this Wi is the H weight of EI, okay? And in the dual problem, you have to change, let's say this is EI. Okay. You have to change the right-hand side to the H weight. Okay. OK， 有问题吗？所以我们刚刚做的事情就是去考虑 matching 跟 verse cover 的关系，包含有 weight 跟没有 weight。然后最后也跟大家讲，就是一般而言，如果你去 Google 的话，譬如说你去 Google matching 的 integer linear program， 它写出来的会是这种形式 ，OK， 它不会针对某一个简单的 example 去设计 ，OK， 所以它一定会写这样子 ，OK，verse cover 它一定会写这样子 ，OK。但是如果我刚刚想要说的事情是，其实你要从这种很 general 的形式去找出它的 dual problem， 有的时候没那么容易 ，OK， 因为就是这里的 left hand side 其实是有一点你要稍微换个角度去想我觉得这个没那么直觉 ，OK， 所以你要直接看出来，从这个很 general 的 form 看出来这个限制，我觉得还蛮困难的 ，OK， 所以我的建议都会是，先从一些 toy example 下手 ，OK， 你有了这个 toy example 之后，观察一下，你这边的限制是它们的性质是什么 ，OK， 那你就比较容易去看出来说这里的 general 的 form 会长什么样子 ，OK， 所以举例来讲，如果你硬要解释的话，你就要去想 ，OK，xi 在这个 weighted combination 里面，就是这个 xi 它是不要忘记 xi 是跟 h 有关的，所以你要想的这个某一个 h 的变数会出现在哪一些限制式里面，所以这是你要去想 ，OK。那如果你对 matching 够熟的话，你就会知道每一个 h 它会出现的限制式就是那个 h 的那两个端点，我再去考虑那两个端点的时候，他们那些端点最多只能选一个边。所以他就会考虑到你刚刚考虑这个 h，OK， 所以在这个 dual problem 里面，你就会知道说每一个 h， 它基本上就是会出现在它那两个端点的限制式里面，所以你就会需要考虑那两个对应的限制式的 dual variable，OK。不过我刚刚讲那是很容易，但是因为我本来就有前面的这些观察了 ，OK， 就是我已经有这些 example， 所以我知道说 OK 这比较像是马后炮的解释 ，OK， 但我相信实务上真的，如果你要有这个转换，我相信一定也都是先从 example 出发，然后有一些猜想，然后再像我们刚刚做的那件事情，就是马后炮去解释说这个为什么是对的 ，OK。那解释其实都很容易的，要解释大家会解释，难的是要把它写出来。你要把它写出来，就是先有一些 example，OK。OK， 所以有问题吗？ Okay, so next, let's consider a different problem. Independent set, okay? Okay, so recall that an independent set is a set of vertices, such that these vertices are independent, okay? By independent, I mean they are not adjacent, okay? So you have to pick a set of vertices such that for any two vertices you choose, they are not adjacent, okay? So for example, you can pick V1, V2, V5, and V6. So if you choose these four vertices, then since they do not adjacent to each other, this is an independent set, okay? And we would like the largest independent set or the maximum independent set, okay? So next we're going to formulate this problem as a mixed integer linear program, okay? Okay, so first step, the variables, okay? So what is a reasonable design for the variables for independent set?所以 independent set 就是我们刚刚说的，你要选一些 vertex， 然后这些 vertex 不能，他们要类似独立，那独立的意思就是他们没有相邻 ，OK？ 你要选一些没有相邻，彼此两没有相邻的点，然后你想要找最大的 ，OK？ 你想要选越多的 vertex 越好，然后希望你选的这些 vertex 都没有相邻。那我们接下来要做的就是跟刚刚的讨论都是一样，就是我们要想办法把它转成 mixed integer linear program。所以我们第一步要决定的永远都会是先决定变数，所以变数要是什么 ？Yeah, okay. So since this time we choose vertices instead of edges, so this time we'll have variables associated with vertices. And once again, we can use binary variables indicating whether this vertex is chosen or not. Okay? So for vertex vi, create a variable xi. Okay? So the physical meaning of xi is that if xi is 1, then this means we choose vi in our independent set, okay? Otherwise, well, we did not choose it in our independent set. Okay, so these are our variables. All right, so we have, in this instance, we have 6 variables because we have 6 vertices, okay? And the next step is the objective function, okay? So what is the objective function? 我们现在已经知道每一个 vertex 我们就有一个对应的 variable 变数 xi， xi 是 binary， 所以只要是1就代表有选，0就是没有选。然后我们想要接下来要做的事情是把那个目标写出来。So this is a maximization problem because we want to maximize the size of independent set. Okay, so intuitively this should be a maximization problem. Okay, and the objective function is simply the sum of the variables, okay? Because this sum is simply the number of vertices that we choose, okay? So if we can maximize this sum, we maximize the number of vertices in the independent set. Okay. So the idea is basically identical to the one for matching. Okay, so in matching, we want to maximize the number of edges in the matching. So we maximize the variables. Okay, but for matching, the variables are associated with edges. Okay, but this time we consider vertices. Okay, so next, the objective function. Okay, so the constraint, the constraint. Okay, so the constraint for independent set is that for any two vertices, they cannot be adjacent. Okay, so how to encode this constraint into an inequality for each edge. Okay. Yeah, for every edge, at most one. Yeah, at most one of the endpoints is chosen. Yeah, but we have to write this as an equality. So what is the corresponding equality? Yeah, so this time we have these variables. Okay. So for example, let's consider this edge. Okay. Let's consider E1. Okay. So when we consider E1, we know that in an independent set, V1 and V4, well, between these two, we can choose at most one. Okay. So we can write this as x1 plus x4 is at most 1. Okay. So if you have this constraint, along with this binary constraint, we know that we cannot have both x1 and x4 equal 1, okay? Because otherwise, if both these variables are 1, then we get 2, okay? And 2 is not less than or equal to 1, okay? So at most one of these variables is 1, okay? Okay, so this is for E1. We can consider the remaining edges in a similar manner, okay? So for E2, we know that x2 plus x4 is at most 1. So that's for E1, and this is for E2. For E3, x3 plus x4 is at most 1. And for E4, x3 plus x5 is at most 1. And finally, x3 plus x6 is at most 1. Okay? And that's it. Okay? So this is the corresponding mixed integer linear program for independent set for this instance. Okay? So we have 5 constraints, okay, each for an edge. Okay? So the physical meaning is that for these 2 endpoints, we can choose at most one of them. Okay? 好，所以这个就是 independent set 的 primal problem 的 formulation. Okay? And by the way, in the problem of maximum matching, we mentioned earlier that we can replace this binary constraint with this continuous constraint, saying that xi is in the range of between 0 and 1. Okay, and I said earlier that you can actually solve this linear program after you replace the constraint. And the optimal solution for the linear program turns out to be integral, okay? So you can actually use the solution with respect to this continuous constraint as the optimal solution for the maximum matching. Okay, but for independent set, we cannot do the same trick. Okay, you can still replace this one with the corresponding continuous constraint, saying that xi is between 0 and 1. But if you solve the corresponding linear program, the solution is not integral. Okay, so because actually independent set is NP-hard for general graph, so you cannot solve it using linear program. OK， 所以刚刚有说 matching 有一个很好的特性，我们这门课没有去讲说 matching 在 general graph 怎么 maximum matching 在 general graph 怎么解 ，OK， 因为那个稍微比较复杂一些。那OK， 那我们刚OK， 然后但是 general graph 上面的 maximum matching 事实上是有演算法，然后 polynomial time 就可以解掉。那其中一个方法事实上就是这个 linear program 的方法 ，OK， 所以你可以把它的 linear program 写出来，然后你把这个 binary 的限制转成这个，那这样子你用 linear program 解出来，虽然说这个你可能想说这个最佳解会不会告诉你 xi 是 0.3。xi 是 0.3 就怪怪，就好像1、3，我只要选 0.3， 那 matching 不能这样子做 ，OK，matching 你要就选，要么就不选 ，OK， 但是就是如果你做这个转换之后，linear program 的 solution 都会是整数 ，OK， 所以你就刚好真的可以用 linear program 解掉 matching 的问题 ，OK， 不过那本质就是因为 maximum matching 它就是 polynomial time 就可以解掉 ，OK， 但是 independent set 就不是这么回事 ，OK。independent set 它是很难的问题 ，OK， 它是 NP-hard， 然后它如果大家有印象的话，我们在讲 vertex cover 的时候，我们有讲，我们可以去，就算 vertex cover 是 NP-hard， 但是我们可以算一个蛮靠近最佳解，跟最佳解最多差2倍的 solution。当然在 independent set 就不行 ，OK，independent set 是非常困难，就连你要去算一个跟最佳解很接近的都很困难 ，OK， 所以事实上，如果你把它做一样的转化，你把这个 xi 是 binary 的转成刚刚那 continuous 的限制，那个 linear program 它算出来最佳解就会是有小数点 ，OK， 所以它就没办法解掉完整的就是 independent set 的问题 ，OK。对，呀。OK， 所以这边有一个关键是 ，OK， 这是一个好问题，就是这个等式，这个等式不一定会成立 ，OK， 在 binary在 bipartite graph， 在 bipartite graph 里面，我们前面花了好几个礼拜去讲 matching 跟 vertex cover 它们大小也是一样 ，OK， 但是在 general graph 就不一样。所以在 general graph 我们就不能透过解 matching 去解 vertex cover。OK， 这样应该要回答你的问题。OK， 所以这个是一个好问题，就是不会是就是你去，特别是这种离散的，因为 matching 真的是只能选或不选 ，vertex cover 也是选或不选。这种离散的问题，你加了这种离散的限制之后，这种等式大部分是不会成立。OK， 那我们这学期前面看的 bipartite graph 上面的 matching 跟 vertex cover 是一个特例 ，OK， 所以在那个特例里面，就算你考虑这种 discrete binary 的版本，这两个一样会是相等 ，OK， 但在你加了很多就是这种 binary 的限制之后，这个等式通常不会成立。OK， 好，不知道大家有没有问题？All right, so next, the dual problem, okay? So once again, let's focus on the constraints and objective function, okay? So let's ignore this binary constraint. 当然。可是既然它
这样这个就没有意义了，就这个解法就。
OK， 所以它的价值不在于说要找一个 match 你的 solution， 它的价值在于，因为它是一个 upper bound， 所以如果你的，我这应该是反过来讲，因为 matching 它事实上是你可以赚到最佳解 ，OK， 所以从这边我们可能要从另外一个角度，我们看 verse cover，verse cover 它是 NP-hard 的问题 ，OK。那这个 primal deal 的转换就会告诉你一个 lower bound， 所以你就可以去拿你 verse cover 的 solution 跟这个 lower bound 去做比较，看你的 solution 跟这个 lower bound 差几倍。对，所以这边的它的价值不在于说它可以真的告诉你那个 optimal 的值是多少，但是它可以告诉你那个 optimal 最多最好好到哪里。对啊，你要做比较，你就可以跟这个最好的那一个比。对，这是它的其中一个价值，这样子。对，那事实上还有一些其他的应用，就是但这门课我们不会 cover， 就是很多时候我们去解设计演算法的时候，我们事实上是会 based on 它的 based on 它的 dual problem 去设计它的演算法。对，所以你有它的 dual problem 之后，你根据它的 dual constraint 去建立一个 primal problem 的 solution。所以你有本来问题你不知道怎么解，你看一下 dual problem。OK， 你在 dual problem 那边想办法maintain 一个 solution， 同一个时间你就可以利用这个 dual problem 的 solution 找到一个 primal problem 的 solution， 也有这样子的演算法的设计，对，这也是应用之一。对，可是这个我们这门课就不会 cover。对，好，还有其他问题吗？因为时间也差不多，那我们就先下课好了 ，OK？ 所以我们就先下课，然后我们3点10分再继续。
个下就是17号，17号要来做测，
当然是现在。
对，就这个时候，他说这个报告说要这个改变。啊，这篇报告上不只说你要讲，你不只要说你要做什么东西，你还要说这个做这个东西准备的时候要criteria。他跟我讲是 letter 嘛，letter 嘛，你说什么？他有些什么？但他英文是大概一个机制，他在国外，但是他也是90年波斯的大牌，然后他回来教书，他的英文不知道他讲什么，他英文，对，因为回归分析是英文说的，然后他就讲一些英文作业去做，他不是说什么用，因为统计学只有1来对吧？就刚好跟一起，我就一起，都是中文，都是然后他就那种讲完英文之后，他就回头讲到中文，他是真的就是讲一句英文，讲一句中文，而且那句中文不是说什么句子 A 句子 B 的，是句子 A 英文，句子 A 的中文，句子 B 英文，句子 B 中文，不是说什么句子 A 英文，句子 B 中文，他不是 A B C D，他是 A B C D， 这种自己到底怎么做？这个超慢的。
还是在换你看对象。
他确实数学教的都是这个，对不对？就不是教那个数学学雅思，同学们讲，我告诉你，一个数学教，这个还讲的是统计学，然后数理统计学，对，除了就没有比较部分是统计学，统计学，不，统计学，心理学，数理统计学，要看会统计，看情况，对呀。
好玩，好玩，都好玩。
浪费我时间。那是不是就要记录？
今日统计，
他全都平时。
那时候上数理统计学的时候，我做这个，然后数理统计学要没去修了。一不用修我们都会。对，我反而觉得，因为我上的是那个3月拍的学习，不是真的过去，然后想说看你的数据好像有讲过。
All right, okay, so given this primal problem, next we're going to find a corresponding dual problem. Okay? And first step, well, always start with the dual variables. So for every constraint, we have one corresponding dual variable. Okay? And since we create these constraints for every edge, this time for the maximum independent state problem, the dual variable is for every edge. Okay? Okay. And then the objective function. Okay? So the objective function is just like the inner product of the right-hand side of the constraint and the variables. Okay. Okay, so this is the objective function. Okay, and then the constraint, and let's start with the right-hand side. So we have one constraint for every primal variable. Okay, so because we use this constraint to enforce that we have an upper bound for the objective function. Okay, so this time, once again, all the coefficients are just 1. Okay, so now we have completed the right-hand side of the constraints in the dual problem. And then let's consider the left-hand side. So recall that this is for variable x1, okay? That is for v1, okay? So we want to make sure that the coefficient of x1 should be at least the original coefficient in the objective function of the primal problem. So let's find out all the constraints that have x1. Okay? Okay, so since there's only one constraint containing x1, and the constraint is for E1, so we only have one dual variable y1 here, okay? Okay, and next, the coefficient of x2. Okay, so once again, x2 only appears in one constraint, the constraint for E2. Okay. So we have y2 in the left-hand side. All right, so next, x3. So x3 appears in 3 constraints, the constraints for E3, E4, and E5. So, okay. So y3 plus y4 plus y5, okay? Okay, next, x4. Okay. Okay, so x4 appears in, again, 3 constraints. The corresponding variables are y1 up to y3. Okay. So I think until this moment, you can all start to have a feeling about this left-hand side, okay? So next, x5, okay? Okay, so x5, okay, corresponding to v5, only appears in 1 constraint. Okay, so I think it's easy to see that for x6, this guy, okay, the left-hand side is just y5. Okay. All right, so after building up this dual problem, we have some observation for the constraint. Especially for the left-hand side. So the left-hand side is just the edges incident to the vertex that we consider. Okay, so for every constraint corresponds to some vertex. Okay, and the left-hand side is just a dual variables for the edges incident to that vertex. Okay, so for x4, let's consider v4, and v4 is incident to these 3 edges, e1, e2, and e3. So we take their dual variables, their corresponding dual variables. They will be the left-hand side. Okay. Okay, so the final constraint, all the dual variables should be non-negative. Okay, so that's your dual problem. Okay. All right, so next is to figure out the physical meaning of the dual problem. Okay, so this time, again, we can add 1 constraint, the binary constraint. Okay, so once again, yi equals 1 if ei, because y corresponding to h, so this means the ith edge is chosen if y is 1, okay? And the objective function says we want to choose the minimum number of edges, okay? So we want to minimize the number of edges chosen, okay? And the constraint says for every vertex, we have to at least pick one of its incident edges. Okay? So for V1, we must pick E1. Okay? This is the only way to cover it. Okay? For V2, we have to pick E2. And for V3, we have some choices. So V3, we can choose E3, E4, or E5. Okay? So one of them must be chosen. So we have this corresponding constraint. Okay. So yeah, so this is just the edge cover problem. So in the edge cover problem, we use edges to cover vertices. Okay. So this is why when we consider independent set, we also consider edge cover. Okay. Okay, so let's try to write down the general form. Okay. So the objective function is the sum, okay? The sum of all the variables. Okay. And we want to maximize it, okay? We want to pick as many verses as possible in our independent set. And the constraint is that for every edge, we can pick at least, at most, one of the endpoints. Okay. So that's it, okay? And if you want, you can also add the binary constraint. Okay, so this is the mixed integer linear program for independent set. Okay. Now for the dual problem, because we have one dual variable for every constraint, and because we have one constraint for every edge, so we have one dual variable for every edge. Okay, and the objective function is just the inner product of the dual variable and the right-hand side of the constraint. Okay. Okay, such that, well, now because we have variables for every vertex in a primal problem, so in the dual problem, we have one constraint for every vertex. Okay. And the right-hand side for the constraint is easy. It is just the coefficient. And since the coefficients are just 1, so we have 1 here. Okay. And next is the most difficult part. Okay. The left-hand side. Okay. But once again, my suggestion is that look at the TOEIC sample. Okay. And try to figure out what is the left-hand side. And the left-hand side from this TOEIC sample is that, well, we just take the sum of the dual variable for the instant edges. Okay. So this is the corresponding dual problem. OK， 所以我们刚刚做的事情就是把 independent set 跟 edge cover 的 general form 写出来。OK， 那唯一想要再次强调的就只有这个最困难的这一步。OK， 这一步是整个 primal dual 的转换里面最难写出来的。我觉得比较容易做的事情还是一样，你先找一些简单的 example， 在那个简单的 example 做一些转换，然后看一下它对应的 left hand side 会是什么，然后你这边就直接写出来。那剩下就只是马后炮的解释，马后炮的解释大家都会 ，OK， 所以那个就很简单 ，OK， 所以有问题吗？有吗？所以很明显，第一次作业当然就会有一些，这个转换让大家练习 ，OK。有吗 ？Right, if not, that finishes our discussion on primordial transformation. Okay. Next, the next topic is still related to matching. Okay, and this time on general graph, but I'm not going to discuss the algorithm to compute maximum matching. Okay, I'm going to just consider perfect matching. Okay. And I won't give you an algorithm to compute a maximum matching, because a perfect matching, okay? Because you can use maximum matching algorithm on general graph to compute a perfect matching, okay? If it exists. So next, the problem we're going to consider is that when does a graph have a perfect matching, okay? Not every graph has a perfect matching, okay? Some graph does not have perfect matching, okay? So we want to find the sufficient and necessary condition for the existence of perfect matching, okay? So let me give you an example, okay? And by the way, we have considered this problem for bipartite graph already, okay? Recall that we have host condition, okay? So for every set, recall that in bipartite graph, we have x and y, and let's just choose an arbitrary set S of x, and we'll consider all the neighbors of S. Recall that we have shown that if the number of neighbors of S is greater than the size of S, and this is true, if this is true for every possible set S, then we have a matching that saturates X, okay? So this is host theorem, and this is for bipartite graph. So next we're going to consider general graph, okay? So these graphs can have odd cycles, okay? So we need a different condition, okay? And yeah, so I'll just restate host condition. So this is host condition. So if the graph satisfies host condition, then we can have a matching that saturates X. Okay. So next I'm going to draw a graph and see if you can tell So this is the graph that we're going to consider, and this is not a bipartite graph because you can see that there's a triangle, okay? So the question is, does this graph have a perfect matching? 所以现在这个 graph 就不是 bipartite，OK？ 然后我要大家用肉眼看，当然会有一些 argument，OK？ 去看出来说这个 graph 它会不会有 perfect matching？ 对，如果有人心算很快，可以 一下暴力解看出所有的 matching， 那不算 OK。我要一个直截了当的 argument 去说明说这个 graph 有没有 perfect matching。OK， 所以为什么？
因为下面4个要有的话，上面那个就必须要上联。
我给它一些编号好了，所以假设这是 V A B C，OK，、
以 C 那个房子为例，
嘿，
下面的4正方形要连起来的话，就代表正方形不能和 C 连。
正方形不能和 C 连。你说下面这4个不能跟 C match， 哈，所以
C 就必须要跟 B 连。
对，
那 C 和 B 连的时候就矛盾，因为 B 不能和 AB 连。那你上面的那个上面2个房子的4方的正方形又必须要连起来，那就矛盾。
啊哈，所以我试着再重复讲一次。你说如果这个有 perfect matching， 所以你要反正吧，你要找出一个矛盾嘛。那如果它有 perfect matching， 你说我们先看下面这4个点，然后如果它们会被 perfect matching saturate， 你说 C 就一定要跟 V 配对在一起，所以 C， 所以整理一下，目前就是如果有 perfect matching 的话 ，C 就一定要跟 V match 在一起。但是你说接下来要发生什么事？
因为 C 和 B 连在一起，所以因为它3个一模一样的组织啊，就3个房子，然后搭一条线嘛。那你既然有占了 C 和 B 了，那剩下2个房子不能占 AB 了，就 AB 都不能和 B 连。
对对对
就。矛盾了，因为你必须要至少要你一个方式要是 perfect match 的话，要 A 和 B 中间那个交点，就 A B C 要和 B 连，才可以那个 perfect match。可是你既然 B C 连了，那 A 和 B 就不能 B 连，这就矛盾。对，就不可能有 perfect match。
OK， 我试着再修改一下，因为那如果是这样呢？所以我觉得刚刚我想要带出来的关键是，刚刚之所以说 C 一定要跟 V 连，有一个关键应该是底下这里，它的点的个数是在刚刚的example 里面，刚刚是奇数，刚没有下面这个，所以下面这边是奇数，所以如果是奇数的话，就一定要对外 match，OK。但一旦我刚刚加了这2个之后，这边就会变偶数，所以它就有这里面它可以自己就 match 起来，然后这边也是一样，它自己就可以 match 起来 ，OK。所以我觉得刚刚有一个关键是奇数还是偶数 ，OK。只要你框一个 subgraph 出来，然后你发现这个 subgraph 的大小是奇数，那你就会知道这个 subgraph 它一定需要往外连，往外 match 才有办法整个，因为我们要 perfect matching 嘛，所以就每个点都可以被 match，OK。Okay, so I guess I'm going to just state the condition for perfect matching in general graph. So the condition that I'm going to state is called Tilde's condition. Okay. Okay, once again, we consider all possible subsets, but this time, because this is a general graph, so we do not have the bipartite sets x and y. So we only have the whole vertex set V, okay? And we will consider every possible subset of V, okay? And I need some notation. Perhaps I'll just okay. So the check that I'm going to consider is first remove the subset from the graph. Okay, so for example, we can remove this vertex V from the graph. And after we remove this V from the graph, we also remove the instant edges. Okay, so after we remove V and these 3 edges, the number of arc components in this graph will be 3. Okay. And the condition says you cannot have too many arc components because it's difficult to saturate arc components. So the number of arc components cannot be too high, okay? It can be at most the size of S, okay? Because for every arc component, it may be possible to match every arc component to some vertex in S, okay? So that's it. So this is called Thieves condition, okay? So let's check, okay? So if you take the vertex V as the single vertex in the set S, okay? Then the number of arc components is 3, while the size of S is just 1, okay? So let's consider this, okay? So if you have 3 arc components, okay? So you have to use some vertices outside these arc components to saturate these arc components. So since there are 3 arc components, you have to use at least 3 separate vertices to saturate them, okay? So this means the size of S should be at least 3. Otherwise, there's no way you can saturate the whole graph. Okay, but this time, the size of S is just 1. Okay? So you can, at most, saturate one of these 3 arc components or houses. Okay? So for example, you can saturate C by matching V and C. But then you cannot saturate A and B. Okay? So to saturate A and B, you have to add more, exactly 2 vertices to the graph so that you can saturate A and B. Okay? Okay, so yeah, so that's it. So I think it's easy to see that if you have a perfect matching, okay, then you must have Thieves condition. Okay? This one is easy. Okay? So what we're going to prove is that if a graph satisfies Thieves condition, then the graph has a perfect matching. Okay? So this is called Thieves theorem. Okay? And I'm going to use this notation O of G. So this is just the number of arc components in the graph G. Okay. Okay, so this is Thieves theorem, okay? So if you have a graph, and it happens to be that if you can test all the possible subsets of the vertex at V, called S, okay? And we compute the number of odd components after you remove S from the graph. This is the left-hand side, okay? And compare it with the size of S, or the number of vertices that you remove, okay? And if the number of odd components is not too high, okay? If it is at most the number of vertices that you remove, then we can show that there's always a perfect matching, okay? So this is Tude's theorem, okay? Okay, so there are, before we prove Tude's theorem, we can test some simple properties, okay? So for example, if a graph has a perfect matching, then what is the number of vertices in the graph? Even or odd? It must be even, okay? So if the graph satisfies this Tude's condition, can you show that the number of vertices must be even? Okay, 所以对，所以，但我听不太出来说这个为什么会变。所以我现在要做的事情是这样，就是如果你手上的 graph 有满足这个限制，就是不管你删掉几个点 ，OK， 你删掉的点就是 S， 你把它删掉之后，你就会有一些 components 跑出来 ，OK， 搞不好你没删就有一些 components， 这也有可能 ，OK， 那不管怎么样，你删掉的点的个数一定会比删掉之后的 odd components 个数更多。如果你有这个条件的话，我们要怎么去说明说那本来的 graph 的 vertex 一定是偶数？不难啊，但是我刚刚我没有办法直接连接到你的 argument 跟我们要证的东西。知道我在说什么？我们要删，我们这里是删掉所有任何一个，你可以删掉0个，你可以删掉全部，你可以删掉随便一个你想要的 ，OK。对，刚刚那个我也听不懂，删掉基数。假如说我删掉那个 S 是3个点，嘿，3个点的话，那它连接的3个 R components， 不一定，它的 R components 有可能是0，有可能是1，可能是2，有可能是3。就这个条件只有告诉你，删掉之后的 R components 的个数就一定最多就是你删掉的个数。所以我并没有说这个 R components 的个数一定会是偶数，并没有。对。我猜我可能因为这个没那么难，所以铁定是大家我表达的不是很清楚 ，OK？ 所以我先把条件讲清楚 ，OK？ 所以这个就是。所以这个 property 叫做 Tude's condition，OK？ 所以你会去测试所有的 vertex 的 subset，OK？ 测试的方法就是很简单，你把这些选出来的点 ，OK？ 删掉，所以这个符号 G set minus S 就是把 S 这些 set 从 graph 拿掉，这也包含我刚刚说的把 S 相邻的边也拿掉 ，OK？然后我们去看它的 R components 的个数，然后这个 check 就会是说这个 R components 的个数最多，它不能太多，因为直觉上来讲 R component 就是很难搞 ，OK？ 它没办法自己 saturate， 它一定要想办法对外，所以 R components 的个数不可能太多，它最多只有你删掉的点的个数，就这样子 ，OK？ 所以我刚刚问大家的是，如果你有这个 property， 你能不能说明你的 graph 一定是有偶数个点？Okay, so if we remove nothing, okay? If we choose S as the empty set. So this G set minus S is simply the original graph, okay? And Thieves condition says this number of R components is at most the number of verses that we remove. But this time, since this is an empty set, it is 0, okay? So this shows that the number of R components in the whole graph is 0. In other words, there's no R components. If there's no R components, then number of verses must be even, okay? So at least we know that given this Thieves condition, we know the number of verses in the graph must be an even number, okay? So that's a good news, okay? But we need more than that, okay? So because even if the graph has an even number of verses, it does not mean that we have a perfect matching, okay? So we cannot finish the proof today, okay? But because we're going to prove this by induction on the number of vertices. So today we can consider the induction basis. Okay, so recall that n is the number of vertices. Okay. Now my next question is, what is the smallest number or the smallest value for n to satisfy Thieves condition? In other words, is it possible to have a graph that has only one vertex and satisfy Thieves condition? No, because we've just shown that the number of verses must be even. So the induction basis starts with 2 vertices, okay? Now, if you have 2 vertices, you have 2 possible graphs. So this is one possibility. And this is the other possibility. Okay, so which one satisfies Thieves condition? So recall that the goal is that we want to show that if the graph satisfies this condition, then it has a perfect matching. And we want to prove it by induction. So we're going to start with some small graph that satisfies this condition and show that this small graph has a perfect matching, okay? So intuitively, we should hope that this graph does not satisfy Thieves condition, because otherwise the theorem is wrong, okay? So because certainly this has no perfect matching, okay? So in other words, we have to make sure that this one does not satisfy Thieves condition. So now, why is that this graph does not satisfy Thieves condition?所以我们要做的事情就是 induction， OK？ 所以我们会从比较小的 graph 出发，从 n 一般来讲，如果 induction 大家会想 n 等于1了 ，OK？ 但我们刚才知道 n 等于1不可能，因为这个 n 一定会是偶数 ，OK？ 所以我们从 n 等于2开始，然后 n 等于2就只有2种可能，就要么是长这样，要么是这样 ，OK？ 不会有其他可能 ，OK？ 我们没有考虑 self loop， 我们也没有考虑刚刚就第一节课有考虑的那种2个点之间有很多个 edge。multi edge 这个我们不考虑 ，OK， 所以你就只有这2种可能性。那只有这2种可能性的情况下，你要怎么怎么证？所以我们要做等一下要做的事就是去看出来说，这个 graph 其实你不用考虑，因为这个 graph 它不会满足 Thieves condition。我们现在证明只需要考虑那些会满足 Thieves condition， 然后再去说，只要你满足那 condition， 你就有 perfect matching，OK？ 所以这个 graph 它为什么不满足 Thieves condition？ OK， 所以一样你可以考虑空集合。So if you take S as the empty set, then the number of components, the number of odd components is 2, okay? Because this is one R component and this is the other R component. Okay, so if it satisfies Thieves' condition, then this should be at most the number of verses that you remove. But this is not the case, okay? Because here we actually remove nothing, okay? So it does not satisfy Thieves' condition, okay? So in our proof, we don't need to consider this graph, okay? Okay. So how about this one, okay? So does this graph satisfy Thieves' condition? Okay. So I think it's easy to check, okay? So okay, so because this is kind of a symmetric graph, so you can remove A or remove B. They have the same effect, okay? So what happens if you remove no vertex from the graph? Then the number of R components is 0, okay? Because the original graph has no R component, okay? Okay, so this is at most the size of S, okay? Because here, in this case, S is 0, okay? Now, if you remove A from the graph, then you have one odd component. And once again, this is at most the size of S, okay? And finally, if you remove every vertex from the graph, then you have actually no components at all, okay? So clearly, this is at most the size of the number of verses that you remove, okay? So this graph satisfies Thieves' condition. And clearly, it has a perfect matching. Okay? So this page shows that Thieves' theorem holds for the case where n equals 2, okay? So this is our induction basis. Okay. So we know that in the proof of induction, next we're going to state the induction hypothesis, okay? So assume that Thieves' theorem holds for n less than k, okay? And then we're going to prove that it also holds for n equals k. Okay. So by induction, by the idea of induction, we finish the proof. Okay. Okay. So in the next 5 minutes, I'm going to just give you the outline of the remaining proof. Okay. So we're going to find a spatial vertex set. Okay, so let's call this vertex set C. Okay, it satisfies several nice properties. Okay, and we can use these nice properties to show that there's a perfect matching that saturates. That there's a perfect matching. That's it. Okay. So the first nice property about this set C is that all the components of G set minus C are odd. Okay? So visually, this looks like this. Okay, so we have the original graph, and we have a spatial set C, and we're going to remove this set C from the graph, and this will create several components. Okay. So let's call these components G1, G2, G3, up to GH. So these are the components you get after you remove this spatial set C. Okay. So the first property says all these components are R components. Okay. And the second property is that the number of components you have is exactly the size of C. So if C has 3 vertices, then after you remove these 3 vertices from the graph, you have 3 components. And all these components are R components. Okay? Okay, so recall that our goal is to find a perfect matching, okay? And these are R components. Okay, so next we're going to show that okay. So the third condition says, say we consider this G1, okay? And we can pick any vertex you want, okay? And remove it from G1. Then the remaining graph will satisfy Thieves' condition. In other words, you have a perfect matching for the remaining graph. Why? Because we have the induction hypothesis, okay? So whenever we have a smaller graph, so this graph has size k, okay? Okay, and because you remove some vertices from the graph, and you actually, moreover, you remove one vertex from these R components. So the number of vertices in this guy is certainly less than k. So by induction hypothesis, if it satisfies Thieves' condition, we can saturate the remaining vertices. Okay? And this is true for every component. Okay? Okay, last property. Okay? So now we have like saturate most of the vertices. Okay? For every component, we can saturate all of them except perhaps this one vertex V. Okay? And also we haven't saturated C. Okay? But now since the number of components is equal to the size of C, we can try to match these remaining vertices to C. Okay? So the last property is that there is a perfect matching Okay, so for every component, we can identify the single vertex that is going to be matched to C. Okay, that is VI. Okay, so for component GI, we're going to match one of the vertex VI to C. Okay, and for this vertex VI, we're going to remove it from the component, and since we have the third property, so we can saturate all the remaining vertices after we saturate VI. Okay, so the final property says there's a perfect matching between C and the spatial vertex VI. Okay, so if we have this vertex at C, we can have a perfect matching. Okay, so let's the overview for the proof. Okay, and that's it. Okay, 所以很重要就是今天晚上我会上传第一次作业。Okay, so tonight I'm going to upload the first assignment, and you have 1 week. 1 week to finish the first assignment, because next week we're going to discuss the solution for the first assignment. Okay, and yeah, so 就这样。Okay.